Welcome. Today we're gonna apply our knowledge about sentence transformer and deep learning to a real-world problem. We have 330 projects, innovation projects going on between academia and industry right now, starting in 2021. And we want to find out if there is some entangled technology within these 330 projects from all participants in the European Union. We start with our typical Jupyter Lab environment, PyTorch, Python. We do not need UMAP, and we do not need actually to import a cluster algorithm, but yeah, just for the sake of it, what I do need is to load up my sentences. In my directory where I have my innovation actions 2021, I load all the different sentences from my 330 projects. And if I have a look at it, it is about 3,387 sentences. And the sentences look like this. Today, we're gonna apply our knowledge. And we define a sentence. We probe our body of documents, our 330 project description, with one sentence. This sentence here, I defined it as established topological antiferrotic system with a novel versatile platform for future energy-efficient nanoelectronics. First I check I have all my sentences. This is my sentence. And then, very similar as we already know, I calculate the cosine similarity of all my embeddings of all my sentences with the embedding of my new sentence. And the embedding of my new sentence, it's easy. I take the BERT sentence transformer model, I encode my sentence, I show the progress bar, and this is it, and the output is clear. Now, what I would recommend to you that you regularly check the manual, because I will show you here from SBERT.net. We have here our pre-trained models, and there are some very good recommendations. For example, if you want to have a look at the semantic textual similarity, the best available models right now are, and just go here with number 1, BERT-base version 2. And this is exactly the model I will load and I will use for my sentence transformer. So here we go. I have here defined my batches of 256 for all my 3,387 sentences. And I guess it will take some time to calculate this on my CPU, and I will be back in a second. And after 2.5 minutes, we have the result. We calculated the embedding of all our 3,387 sentences. We calculated the embedding of our new sentence, our query sentence if you want. And you see here, my sentence was this one. And as you can see now, it is part of a sentence that is within the document. The only difference here that there's the word success in front of this sentence. So this is sentence number 1415. And if you keep in mind that we have about 3,300 sentences and we have about 330 project description, you know that on average there are about 10 sentences describing each and every project. And if we have 1,415 here, sentence number 1,413 is in a close proximity within the project description. So this second sentence, as I found, sounds really nice. And of course, there's sentence 1410, also belonging to the original project description, describing the system. But 1407 also. But what you see here, there are other projects, other sentences with a very similar sentence embedding found by the system. So you can now, as a next step, for example, have a look where these sentences belong to which projects and see if on a meta level of a project description, there would be a reason to cluster those projects together and maybe create a better platform and not let them operate in isolation. But this is the topic of another video. So this has been done very simply by just calculating the cosine similarity. We imported this function from sklearn, but now we're gonna apply some asymmetric semantic search on it. Remember sentence transformers, the sentence embedding. SBERT has some special tricks up its sleeve. And if we have a look at the API, you see that there's especially the symmetric versus the antisymmetric semantic search, yeah, of course. And you see here, there are all the APIs you need, optimize whatsoever. We're gonna apply it now. So at first, here we have let's say we have an asymmetric question, and there's a special BERT model recommended by the author. We're gonna apply this model. We're gonna now embed our 3,387 sentences with this specific distilled BERT model. And what we have a look at then is a special combination of queries. We just calculated one sentence and then compared those one sentence to the other 3,387 sentences. Now, no problem at all to do a for loop. We define 3 sentences. And if you apply a little bit of human intelligence to your artificial intelligence system, you can see that you can create something like an entangled technology or platform question. Like, first interrogation would be a new topological system for nanoelectronics. Which of your ongoing projects have the topic of develop new topological systems? Then you can ask about a biohybrid system technology based on nanotechnology, sensor development, for example. And if you're really interested in the application of this new technology, of this new sensor in an environment, you can ask, is there a sensor application really planned or in the foreseeable future for your, let's say, urban environment monitoring? So the embedding has been done. These are our 3 sentences from our enmeshed query. We apply now this MS Marco, distilled BERT-base version 2 model, and simply we let the system calculate our answer. And here we go. So for the first query, you remember the first sentence, and this sentence is identical to the sentence we just did decoding. We see here that our tensor indices also are 1415, the sentence 1415, second most important sentence 1413, then we have the sentence 1410 and the sentence 14.7. And if you compare this 14.15, 14.13, 14.10, and 14.07, so you see, yes, we checked, these are the sentences, we get the same result. Well, yeah, of course, we use the different utility, PyTorch cosine similarity, for our query embedding of our 3, or our one of our 3 sentences, and the other 3,387 sentence embeddings. So, of course, we expect the same results. Now, if you have a look at the answer of the system, and you have now the second query, you can do exactly the same. You have a look at the project, at the sentences that are returned to you by your system, and you can have a look at all these 3 segments of sentences and combine and get some understanding of the deep knowledge that is going on in R&D and innovation right now. But this is not the point what we're interested in. I want to show you, if you have now that we applied an asymmetric search, what happens if we have now a symmetric model. And this is recommended by the author of SBERT. And he tells us, listen, there's a paraphrase training of Roberta I would recommend for the symmetric case. And we can apply the symmetric case because if you have a look at our queries, I think our queries very clearly qualify for a symmetric research, for a symmetric response from the system. because the length we get as a reply from the sentences are absolutely comparable. So now we can do a symmetric search, as has been already implemented in SBERT by the authors. We calculate our batches for all the 3,387 sentences with our new model. We have, of course, the same 3 query sentences and meshed query sentences, a kind of multidisciplinary query you start on your system. And we're going to use, again, the utility that is part of SBERT. And oh yeah, maybe I didn't show you. Hold on a sec. If I just go back. If you didn't notice here, when we load our SentenceTransformers, we have our SentenceTransformers under utility. So here we go, Asymmetric and mesh queries. You see it takes about a minute and something to do. That's quite fast, this system. 1 minute 20 seconds system. Hey, that's nice. And if we perform our query, we get a result here. 1450, 1410, 1413. Those are the sentences we get as a response from the system. That was 1407, if I remember correctly. Oh, 1406, interesting. Gets another sentences. But you can see now, those are more or less clustered together. So the project description of the specific sentence has now really all the surrounding sentences, 15, 10, 13, 06. Interesting, not 1407, but of course, it's a different pre-trained model that we apply here. The paraphrase is still Roberta, bigger model, a longer trained model, and the still BERT here, they recommend especially for the asymmetric search. So you optimize your search parameter, you optimize your search model that you load, you perform the sentence embedding, the sentence transformer operation, and you will get the significant correlated sentences to your specific query. And if you combine it in an intelligent way, you get a hell of a lot of deep knowledge extracted out from quite a lot of sentences. If you do it like me with 3,000 sentences, it is performed within seconds, but of course, and I just want to show you, there's also a methodology for huge data sets. If you do it with 3 million sentences, or you have a body of knowledge of about 30 or 300 million sentences, you have to split up to parallelize the query chunk size. So here's 100 queries will be performed in parallel, and the corpus, let's say 3 million sentences, are split up in batches of 100,000 sentences. And with this methodology, also part of the utility within semantic transformers, you can sequester yourself through the huge corpus and do the parallelization depending on your system memory, on your GPU acceleration, and so on. So also, if you have a huge amount of text, no problem. There's a very simple methodology. You can perform it on a GPU accelerated system, or you do it like I have done it here, only on my CPU. Thank you.